Mhm. Yes. In Greek atoms in tweezers, atoms in tweezers. I do. With Cindy Regal since 2010.
All right, guys. I think we can get started. Welcome to the second day. It's my pleasure to introduce Maria Rey from JILA, University of Colorado Boulder. So just to get started and get an introduction to our speaker, I'm sure that many of you works with non-equilibrium many-body systems. You work maybe with a simple spin Hamiltonian or a simple bosonic or fermionic Hamiltonian, and maybe you like to add dissipation on it. And basically the reason why we can write down these models and we can believe that non-equilibrium dynamics is real and not a product of our mind is because essentially the work of people like Anna Maria. So this is the field of quantum simulation, right? So the capability, the fact that you can really write down these objects and you can follow their non-equilibrium dynamics. And just to give you a perception of the impact that Anna Maria gave to the field, the pioneering experiment was in 2002, her PhD was in 2004. She started her group at JILA at 2008. So she had basically, over the time of 20 years, the capability, the ability, and the determination to forge the field. So I was trying to count with her the number of quantum simulators where she could contribute. And basically there are 5. So she was impactful on polar molecules, ultra-cold atoms, and optical lattices, cavity QED, trapped ions. And she has the ability to work with experimentalists in a way that is very unusual. So I had the pleasure to collaborate with her, and I've seen her giving advice to experimentalists how to calibrate a laser or how to do a measurement or how to change a measurement protocol. So she doesn't just feed the data. She is mentally inside of the lab. We are happy to have her here because she's also a role model for South America. So Anna Maria Rey was born in Colombia, and she was born at a time in which things were tough in her country. She studied there, and she could emigrate to the United States in the late 90s, where she went to the University of Maryland and NIST. She did her PhD. She went then to Harvard as a postdoc. And after 4 years, she started her group in JILA. If you go to the Wikipedia page, you can see the list of prizes. They would maybe mean not so much to you because you are young, but maybe you can appreciate that this was also fun for me. There are years in which they cluster in blocks of 3 and 4. So sometimes like they condense, they Bose condense. And they are all very important prizes in the community. They testify her impact and the way she could lead the community. So I, as I said, had the pleasure to collaborate with Anna Maria in the past. She's a person with great determination, great commitment, and I'm happy she can be here and can teach you something, and you can merge with her and their very positive mood and attitude. So please, Anna Maria, you have the floor, and you can lead your lecture.
Yeah, thank you, Jamir. But very, very kind introduction. It's very touching. I appreciate it very much. It's really a great pleasure for me to be here. I have been in Brazil before, but never in Sao Paulo. So it's a really great pleasure to be today in this audience trying to teach you a little bit about atoms and light. Yes, I wanted to make this lecture as interactive as possible. I want us to learn something, and that at the end you can say, oh yes, I understood that. So please stop me if you don't get something. It's going to be a lot of discussion. I'm going to ask you questions. I'm going to give you homework. And in the tutorial we solve some of them. So yes, so I think the goal of this is to us to have fun and learn. That's what I want for this lecture. All right, so now the topic. At the beginning, I was very ambitious. I wanted to cover many different platforms. I gave up. So the lecture is going to be only on alkaline air atoms, clocks, and for that, atoms and light. So Let's see if so the agenda for today, I would like to start to give you a brief overview of alkaline air atoms and atomic clocks. This is going to be the first part of the lecture. Then I'm going to give you an idea of why we care having many atoms in a clock, and then why we care about their collisions and some insights in the way that these atoms collide. Then I will explain what is SUN means here. And then I'm going to tell you a story of how we are using the understanding of these collisions to make clock better. So I'm going to tell you about density shift in spin polarized gases, because the clocks are spin polarized. Then I'm going to tell you how the clocks, this likely is going to be in the next lecture, not this morning, SUN orbital magnetism, spin orbit coupling, Warnier static state clocks, and well, hopefully, I don't know why this is not working so well, so maybe I go closer here. And if I have time at the last lecture, I'm going to also tell you about similar ideas that Subir was talking about, but now in the perspective of metrology, that is super exchange interactions. Okay, so let's start with our friends, because these atoms are our friends. And for that, we need a periodic table. And what we're going to talk today about is alkaline earth and like atoms. Alkaline layer atoms, as you remember, are atoms that are in the second column of the periodic table, that has two outer electrons, two valence electrons, but we're also going to include other atoms with similar atomic structure, for example, here, ytterbium. And the reason why we care about these atoms is because they are going to be our best candidates for clocks. I'm going to explain why. Many of these atoms have been able to, people have been able to cool them down. Of course, our favorite at JILA is strontium, but calcium has been cooled down, and also there is some progress in trying to cool down magnesium, and mercury, and a little bit of barium, but very little. We are talking about these atoms with two outer electrons, and when we are trying to focus on the fermionic isotopes. And the reason is that fermionic isotopes have, of course, fermionic statistics, but also they will have nuclear spin I. So not only we care about the electronic structure or the electronic properties, but also the nuclear. And it happens that, for example, strontium have an I equal to 9.5, ytterbium has an I equal to 5.5, the 173, and there is another isotope of ytterbium that is 171, that is 1.5. Now, if you look at the pattern, you are going to see here that we are talking about, when we talk about fermionic atoms, we are talking about an odd number here, atomic number here, 87, 173, 171. And the first question is that we'll ask you is why? How would you know if I give you an atom in the periodic table if it's fermionic or it's bosonic? For example, if I give you rubidium 87, actually it's bosonic. So why? Why? How do you know? Anyone?
So I'm not completely sure, but in the case of the rubidium 87, you have 87 fermions in the nucleus and a single fermion, which is the electron, like in the valence band. So maybe that gives you an even number of fermions, so you get a boson.
Well, it's I mean, maybe related, but not exactly. So I think the answer is the number of neutrons. We have neutral atoms, so we have to have the same number of electrons than protons. No way. So what distinguish then, I mean, therefore, this, because both are spin 1/2, then they don't tell us about the structure. But what matters then is the number of neutrons that can change. So in the case of, for example, alkaline atoms, we have two valence electrons. That means the number of protons have to be even, because you have two. And that means that the number of neutrons is what determines if you have a fermionic atom. If you have odd number of neutrons, there you have a fermion, and if you have even number of neutrons, you have a boson. The situation, of course, changes, for example, when you have alkali atoms. Why? Alkali atoms, you have only a single valence electron, So therefore, you are going to have odd number of protons. And therefore, if you have odd number of neutrons, then you have a boson, and the other way around. Yes? So that's why for alkaline atoms that you have even number of electrons, then all odd atomic numbers are fermions. Now, there is something unique that is interesting, that for the case of bosonic isotopes in alkaline atoms, they have a unique property. They have even number of protons and neutrons. And then this, because of the structure of nuclear properties, it enforces to have I equal to 0. So bosonic isotopes in alkaline atoms, you can never have an I. You know that they're going to be I equal to 0. On the contrary, in the case of fermions, we will have a finite I. And this is going to be key in our story. Why? Okay, so let's now look at the atomic structure. And I don't know if you remember, but when we are going to write the atomic structure, we're going to characterize the atomic structure by 3 numbers. You're going to have the L, the J, and the 2s plus 1. Yes? And if we look at the alkaline atoms that we care, so we're going to have, because you have 2 outer electrons, the lowest energy level is 1s0. That means that is J equal to 0, L equal to 0, and then you're going to have a singlet state. This is the ground state. Now, in order to try to understand the atomic properties, how we're going to interrogate this atom with light, we're going to look at the properties of the low line excited state. So when we look at this next excited state, it's a triplet state, L equal to 1 and J equal to 0. Now, can we use light to drive this transition? Can we use light to drive an atom from here to here? Well, first, it's an optical transition, and we are going to see the wavelength is 698. I try to put here a picture for you of the spectrum, and we are going to see its light here. It's close to a red light. Now, then you can nevertheless start to think that this is a little bit weird, because this transition is 0, J equal to 0 to J equal to 0. Forbidden. Yes, remember, from couplings, matrix elements. And you have singlet to triplet, forbidden. So in principle, this transition should be forbidden. On the other hand, we can see that I'm reporting here a lifetime is super, super long. I mean, yeah, it's between, 100 seconds, 118 actually measured more recently. And therefore, this transition is allowed by the nuclear spin. Otherwise, it would be forbidden. I'm going to explain that. Actually, there is another very relevant transition that we use for clocks, that is this 1p1. This is, of course, allowed, J equal to 0, J equal to 1, singlet to singlet. This is in this 461 nanometer is a blue light, and sometimes when you see a picture of atomic clocks, you see a very beautiful blue light. That is how their experiments try to cool these atoms. Okay, so let's think a little bit more about that. So we are going to have this 1s0 and 3p0. They are called, yes?
So what is the 2 particles in the drawing? Is like nucleons or electrons?
Sorry, can you?
The 2 particles in
These
each
2
of
particles,
these.
I'm talking about the valence electrons. I'm talking about, because the properties of the atomic structure is determined by the valence electrons. So I have 2 outer electrons, so I'm driving 2.
Okay.
And these characterize everything that is filled inside the core. We don't care, and it's the 2 outer electrons that is telling me the structure. So that's what I'm quoting. Of course, ytterbium is a little bit more complicated. That's why it lies in this corner of the periodic table. But for all what we are talking about, let's think about just 2 outer electrons that characterize the structure.
Okay, thank you.
Okay, so I was saying that these 2 transitions, for initially, before I explain more, is almost forbidden, yes, because we can say the matrix elements are not allowed directly. And that's why we call these states clock states, because it's going to be a transition that is going to be super, super long-lived. If an excited atom in the excited state is going to take very long time to decay. And that's what we want for clocks. Because if you think about a clock, and we are going to go into what a clock is later, but if you think about a quality factor, like in classical terms, you wanted to understand what is the ratio between the ticking rate and the damping rate. Yes, and the ticking rate in this case is associated with an optical transition that is of order 10 to the 15 hertz. And a damping rate that in this case is the order of 100 seconds. You put these numbers and it's a quality factor larger than 10 to the 17. So if you try to connect with a classical pendulum, it's going to be a pendulum that when you start let it swing, it would swing for the entire edge of the universe before damping. So that's the type of systems that we are talking about. So now let's try to understand a little bit more why is this transition allowed, and for that I will require looking at the nuclear spins. So as I said, we are focusing, for example, in strontium, we have a finite I, in this case is equal to 9 half. That means you have 10 additional levels that you care about. And for that, I mean, we are going to play with them later. But at the moment, what I'm going to tell you, explain very briefly. Of course, I cannot enter in details. If you want to look at details, you can read a very nice thesis by Martin Boyd from JILA. You just type Martin Boyd JILA, and it's going to tell you all the properties of this structure, atomic structure. So here, I'm just writing the different levels. And the point is that, I mean, let's go here. And you can see that the 3p states, I have 3p0, 3p1, and 3p2. And this is because of fine structure, yes, we're going to have an state that has j equal to 0. I mean, if you have a triplet that is spin 1, spin 1, yes, is here 3 is 2s plus 1, spin 1. And then you have L equal to 1. When you sum the properties of the angular momentum, you can have 2, 1, and 0. So these are these three states that we have, and that are there. We have in additional the singlet P naught. And because you have L equal to 1 and L equal to 1, there is a little bit of a spin coupling or a spin orbit coupling between these two. But if you look at this state, there would be decoupled, as I mentioned, respect to the 1s0. But there is fine structure, a hyperfine structure. So there is the nuclear spin here participating. There is the matrix element I dot j. And these matrix elements introduce some finite couplings between the 3p0 state here and this other state here. So the 3p0 is not purely a 3p0, but because of finite structure, hyperfine structure, hyperfine, I mean, this involves the I. Then we're going to have couplings with all these other states that are allowing to introduce a little bit of coupling. So that's why this transition is not forbidden, is there, is super slow, and this is what we are going to use for clocks. The question, what happens with the strontium-88? Is this a fermion of a boson? A boson, and because of that, I is equal to 0, and this transition is forbidden. There are clocks now that operate with 88, but for that they have to add a very strong magnetic field to mix the levels, so it's more complicated. So having hyperfine structure is a blessing, and this is allows to below these states. Okay, so now I told you these are very long-lived states. They are barely decaying, 100 seconds lifetime. So let's try to think, I'm telling you about clocks. So we all know what a clock is, yes? A clock is something that measures times and therefore has two main ingredients. The oscillator, what ticks, and the counter, that is what we use to count the oscillations and with that translate to time. So we are used to pendulum clocks, I mean these quartz clocks, everything operates that way, including atomic clocks. So what is the difference? Oh,
So in this quality factor, there was a factor of
Yes.
the energy level of the gap, right? So can't you just take a much higher level, excite with
excellent.
microwave,
Yes.
and then
Yes. I mean, the best clocks now that exist in the world are thorium clocks. that use a transition that is 100 times larger. The problem is how you couple and how you develop lasers at this wavelength. That is non-trivial. So it exists, but the technology for develop these types is really complicated.
So is the terahertz range or?
No, above. It's hundreds of terahertz. I mean, terahertz is 10 to the 12, yes?
Yeah.
We are 10 to the 15 here. It's going to be more 10 to the 18.
Okay.
It's a nuclear transition.
Okay, thanks.
So, yes. But in principle, the higher, the best, if we could. Okay, going back to my clocks. So in our case, what oscillates, what ticks is an electromagnetic wave. And what counts the oscillations are the atoms. So actually, the clocks that we are talking today about are clocks so surprising that not even actual electronic devices can record the oscillations because they are so fast. Optical transition is so fast for electronics to count them. The only thing that can count these very fast oscillations are the atoms. So that's something unique. So this is what we have, very simple, and we're going to explore a little bit how with these ingredients, a laser and an atom, we're going to build an atomic clock. If I can change, okay. So the interesting part, or why we build atomic clocks, is because we need an unrivaled definition of the second that is universal. I mean, because if I make this clock, I mean, it's math-made, and it can tick different depending of the material, depending of many things. But quantum mechanics allows actually to use the quantization of the energy levels of an atom as the universal fundamental definition of the second. And in fact, the first atomic clock was built in 1955. It was a cesium clock, and still today, the definition of the second is based on the cesium atom. We define the seconds as about 9 billion, I mean this number, of oscillations. How we take for a frequency that is resonance with two energy levels of cesium, and 1 second we define as this number of periods of this radiation. However, cesium is not the best clock in the world, and we are about to change it. Very soon you will see a change from cesium to other atom. And going back to the question there, why cesium is not the best? Well, the quality factor argument, or very simple, this ruler argument. If you have a ruler with some ticks and another ruler with more ticks, which ruler are you going to use to measure more precise? Well, the one that has more ticks. Similar thing happens with clocks. More ticks, higher resolution. The problem is that cesium clocks, the ticking uses microwave transition. It's at 10 to the 9 energy splitting, so this ticking is really slow. It's convenient because electronics can measure. But on the other hand, these optical clocks have the advantage that we have ticking that is 10 to the 15, as I mentioned before, hertz, and therefore the ticking is super fast, and we can have a precision that is much higher. The drawback is that we need how to manipulate these atoms, because there are various complications. First, the transition is super fast. We need how to read it. Second, because it's high energy, when an atom absorbs this photon, it's going to recoil because the momentum imparted by the photon on the atom is super large. So we need to learn how to trap the atoms. And we need now to develop the lasers that are going to take advantage of this very narrow transition. Okay, now some terminology that I always find confusing, so I just wanted to emphasize it here. There are two ways that we characterize how good a clock is. We are talking about accurate clocks, and we are talking about precise clocks. So accurate is how specific, how good are the clock to reporting a given number, yes, a given frequency. On the other hand, precise is the statistics, how coherent are the numbers that I'm reporting. Of course, I want both, but sometimes there are clocks that are more accurate, there are clocks that are more sensitive, and what we want to build, of course, is the most accurate, sensitive clocks. So I'm bringing this down because if you are trying to look at the clocks that are the state of the art, of course, we are going to have optical transitions. I'm excluding the thorium clock because it still is under development. But if you look at the state-of-the-art clocks, are alkaline air atoms, and they have nevertheless, you can see a plus here. They can be ions or they can be neutral. And I'm quoting here some different labs along the world. So Japan, France, this is US, Germany, Canada. Well, there are different labs around the world that have the clock, most accurate clocks. At the moment, the record is the aluminum clock. Actually, this year, the aluminum clock reported an accuracy. Look, an accuracy of 5 × 10⁻19. This is crazy. But the disadvantage of this clock is that it operates with a single aluminum ion. On the other hand, neutral atom clocks can operate with thousands of atoms. These have reported an accuracy of 10⁻19. So it's not as good as the aluminum, but it has high stability, high sensitivity. We are operating 10⁻3, 10⁻4 atoms. And you can see this is 10,000 times better than the cesium clock. And what I want to emphasize here is, look, this is the cesium fountains. This is the progress that we are having across the years on alkaline atoms. It's impressive. It's like a Moore's law. I mean, it's really a Moore's law. What is the one that is exponentially improving the size of computers? What is this law? Well, Moore's law. Okay. So I was correct. Yes, so it's exponential. It's really, really, really important. And I think we are going to start reaching a point where it's going to stop. And this is going to enforce us to actually start to use entanglement. And maybe Nicolo is going to tell you a little bit more about that. Okay, but just to give you a number again, to understand, you are saying 10⁻19. At 10⁻18, we were saying that we were building a clocks that neither lose or gain 1 second in about 15 million years that is there of the universe. Super, super precise, super precise. So what I'm going to start doing is tell you a story how we did to generate a clock of this precision. And for that, we need many body physics, we need atomic physics, I mean, we need a lot of things. And the exciting part is that this clock is not only useful for measure time. This clock is going to be the state of the art with quantum simulation and many other things. So we will go there. Okay, yes, I just wanted to emphasize that it was very exciting that this was happening in June this year. So we're improving a lot. Okay, so let's go how we're going to build our clock. As I said, we need an oscillator. It's going to be the laser. We need to have atoms that are the counter. We need to trap them because, unfortunately, this is an optical transition and the atoms are going to actually blow away if we don't trap them. So this is something that we have to take care. And the most important part is that we need to build a feedback loop that I'm going to lock the frequency of my laser with the frequency of the atoms, because that's what we need. The atoms are the counter, and we need to lock my frequency. So, okay. So let's look about how we're going to do that and what the typical spectroscopy that we use to actually lock the laser to the atomic transition is called Ramsey spectroscopy in honor of Norm Ramsey, that he won the Nobel Prize in 1989. So maybe I wanted to raise hands who know what is Ramsey spectroscopy or who is familiar with Ramsey spectroscopy. Okay, not so many. Okay, that's good that I'm covering it because it's the key. It's fundamental. I mean, if you learn Ramsey spectroscopy, you know a lot of atomic physics, so it's very important. Okay, so we're going to consider a two-level atom. Yes, ground and excited state. I have a frequency that is omega naught. And what I want to know is how, when the frequency of my laser is equal to the frequency of the atomic transition. That means locking my laser to the atomic transition. Okay, we call a quantity that is called the tuning. That is the difference between the laser and the atomic transition, delta. Okay, so the Ramsey spectroscopy consists in 3 different steps. Well, I have to learn and this is going to be another lecture, how to cool my atoms, how to optically pump the atoms, but imagine that all the atoms start down. Yes. Now what I'm going to do is I'm going to illuminate the atoms with a laser. So I'm going to illuminate the atoms with a laser, with a strong laser. So who here know about Bloch sphere? Okay, great, exactly. So in the Bloch sphere, all atoms start down in this situation, and then I'm going to apply a pulse that is going to drive, the pulse is going to be written by this Hamiltonian, omega Sx, yes? Omega Sx is going to introduce a rotation on the Bloch sphere along the x-axis. This is the x-axis. Sorry, this is not showing. This is the x-axis, so my arrow is going to go from down to some place in the zy plane. And as you can see here, this is the vector of the spin. Has no component along the x direction because it's rotating along this axis, and it has some component along the y and the z direction. Yes? Okay, now the x appear. So this is the first, and I'm going to call theta equal to omega times t. I'm applying the laser for some times. This is called the pulse area. So this is going to set the orientation of the Bloch vector after the first interrogation. Here, for example, I show pictorially because it's easier when theta is equal to pi half. So I have a Bloch vector pointing along the y direction. Now, the important part is that it's always good to go to the rotating frame of the laser, yes? So what happens is that in the rotating frame of the laser, if the atomic transition is different from the clock transition, the Hamiltonian that rules the dynamics is that the tuning time is c. That means that a spin up is going to have a frequency that is plus delta, or because of the minus sign, minus delta, and a spin down is going to have a frequency that is plus delta. So they are going to acquire a different phase. This different phase, you can see if I write S minus operator, that measures the different phase accumulated by the up and the down state, is going to start to precess at this frequency delta, yes? In the Bloch sphere, what it means is that I'm going to start accumulating a phase during my precession. I'm going to start to rotate at fixed SC. SC is conserved, and I'm going to start to rotate accumulating some phase. Yes? All with me? Then I'm going to I wanted to read this phase. Because this is the information. If I read this phase, I know when my laser is going to be locked to the atomic transition. How I read it? I cannot read a phase. In the experiment, I can measure population. How many atoms are in the excited state? How many atoms are in the ground state? So how I translate this phase into population? The experiments, they apply a pi half pulse here. And the pi half pulse then translate after this pulse. If I measure SC, that means the population difference between atoms in the excited state and in the ground state is going to have a term that is cos delta t, and therefore I'm going to have what is called as a function of this delta tau. Tau is the time of the dark time. There is no laser during that time. And this delta tau, you can see I'm going to have these fringes, and these fringes are going to tell me the information that I wanted, that is the tuning of the laser with respect to the clock. So that's how we lock a laser to an atomic transition. There are other ways. There is Rabi spectroscopy as well, very similar. But for this time, let's focus about that. So you have delta and you have tau, and therefore you can see this phase difference is telling you how much I have to steer the frequency of my laser until it's locked to the clock. And it's important that these oscillations last very long, and that's why I need a good atom, because if the atom decays very quickly, then these fringes are not going to be present and I cannot measure. So the longer the lifetime of the atoms, the more precise I'm going to be able to measure this frequency and therefore have information of the energy splitting.
But is that universal? I mean, doesn't it depend on? I mean, you didn't tell us what G and E is. If they have like spin, or if the
G
light
and
is
E
if
are
is the
going
light.
to be the clock transition. This is exactly in this
Okay, but
talk.
doesn't it depend on whether the light is polarized or if it's a fermion or boson or something?
Okay, so it's very good point that when we have many atoms, there are going to be systematics. This is something that I'm going to control. At the moment, what I'm trying to emphasize is that if I have a strontium 87, ground is 1s0, E is 000, and I'm going to use this frequency, the frequency, as the standard. Not at the moment, but in the future, for example, the strontium is the energy standard, is the frequency standard. So I'm going to measure, what I need to know is what is this omega naught. So for that, I'm going to lock a laser to this transition frequency, and this is what is going to be used as a standard. So
Okay.
there are systematics. There are going to be systematics. There are many levels, as you said, and if you are going to have magnetic field, it's going to introduce systematics. There are going to be, there are a lot of things that clock has to control to report this fundamental frequency and not something else. But just if you control all these systematics, then it's universal.
Okay.
So
Thank you.
what else you are thinking that could not be universal, for example?
I mean, I don't know. I don't. I mean, there's no Hamiltonian or something. I mean, I guess if you couple something to light in the weak coupling, it's some dipole coupling,
The
right?
dipole coupling,
But
exactly.
it
Perfect.
depends on what your ground state looks like.
Yes. So, but I mean, this is a very good point. And for that, let me go back to, that's why it's important. Okay, let's go back here. Here. We are talking about 1s0, 3p0. Yes? The dipole moment is going to be associated with the coupling between these two states. Yes? The dipole moment is going to be fundamentally connected with the line width of this atom. So the line width is proportional. This line width is proportional to the dipole moment squared omega cube. Yes, so it's going to depend on the atoms, but I know this is fixed, this is fundamental, this is given for this atom, and therefore, I mean, there is already, this is set. The dipole moment of the transition is set. So, but I think all these properties are going to be the same for an atom here or an atom in China. Is fundamental. So that's what we are going to use. The energy splitting is fixed. The dipole moment between these two transitions is fixed. It's a natural property. And then what we are going to do is that we're going to use light. So I'm going to, when I write omega, maybe that's what it was missing. When omega is proportional to the electric field that I use with my laser times the dipole moment of the atom. So omega can change, but it's not important because that's not the quantity that I'm measuring. The quantity that I'm fundamentally measuring is the difference between my laser minus the atomic transition. This is what I call the tuning. And this is what I'm getting information for.
Okay, that was Crescent. So I need to have a ground state that has a finite dipole. Otherwise.
Oh yes,
okay.
and that's why we need our I. That's what our nuclear spins are the salvation. Because without I will not be able to have a matrix element. Without the nuclear spin, when I was saying that the atomic is forbidden, the atomic transition is forbidden, is that there is no dipole moment. That's what, maybe I was not very specific. Forbidden means that no dipole moment. Allowed is dipole moment, and when there is dipole moment, there is a lifetime of the atoms immediately, because then the atom in the excited state can decay to the ground state. This dipole moment is very tiny, really tiny. That's why the lifetime is so small. The lifetime is of the order of millihertz. In contrast, maybe I want to emphasize, if you look at the lifetime of this transition is dipole allowed, and it's going to be 34 megahertz, huge. The transition between 1s0 and 3p1 is going to be 7.5 kilohertz, much bigger. This transition between these two is going to be millihertz. And tiny, but useful because it's just because the delta E, delta T, yes? Oh, well. Then in this case, you can see that the longer the lifetime, the better, the smaller the resolution of the energy. And that's what we want to do for clocks.
Thank you.
Mm-hmm. Great, great. Excellent. Yes, please interrupt anything that is not clear, because that's the purpose. Yeah.
So for measuring the detuning, you start, I guess, varying the frequency of the laser, and once you get like your population, like one of these peaks of the cosine, then the detuning would be 0, but it's a cosine. So how do you know you're in the 0 detuning and not like the 2 pi detuning?
This is very important, and this is fundamental. That's why one of the biggest, this is called dynamical range. And actually, this is one of the nightmares of clock. And that's why typically the time that you interrogate cannot be so long. Because ideally, you are going to interrogate as long as you want. There is the constraint that you cannot script a fringe, because if you script a fringe, you are screwed. Yes. So there are various attempts to try to increase the dynamical range. At the moment, there are various strategies, but I mean, clocks don't, because of systematics, we are not pushing, I mean, we're not limiting that for classical. When you're starting to operate with a cat state or something, things change and you have to be more careful. But for the moment, we are not so limited by that. But it's important, definitely. Good point. Okay. So we have our Ramsey spectroscopy. And if you want, I mean, I think for homework problems, it would be nice if you make sure that you can derive all these formulas. We can derive them more carefully later, but it would be nice if you do it. Now, I was saying that the difference between neutral atoms and ions is that we can interrogate many atoms. Yes? And why is that? Well, because I have more atoms, better signal to noise, and therefore I have a better clock. But then the point is that we are going to start dealing with systematics that are not present in a single atom. So instead of one spin, if I have many spins, I have a much larger arrow, and therefore my signal increase. And if I have uncorrelated particles, I have a signal to noise that increase by a square root of n. So I wanted to push n as large as we can. Yes, that's the goal. So you can see that the signal increases with n here of the Ramsey. Okay. So for the moment, I'm going to tell you a story about spin polarized clocks. So imagine that our two levels, the ground and the excited state, are going to be these 9.5 states, nuclear spin 9.5 state. And let's try to build a story about that. So first, of course, we are going to make sure that our laser is the best. And we are going to make sure that something that is called, if my atoms are very cold, then the atoms are going to not be subject to what is called Lamb-Dickey parameter. So I think the point is that, maybe I go into that later, but I mean, if you think about the Ramsey spectroscopy, ideally what I want to have is all atoms experience the same Rabi frequency. Yes, all atoms experience the same Rabi frequency. So we are creating a very pristine pi-half pulse. And then I have all atoms experience the same detunings. In which way I cannot experience the same detuning? Well, we know about the Doppler effect. If I'm running, I'm going to experience very different frequency if I'm standing up. So in order, laser cooling and cooling the atoms is fundamental. And actually, the story of ultra-cold atoms started because we wanted to cool the atoms to build better clocks. That's how it started. So we need to cool them down to avoid any Doppler shifts. And now we have to trap them, because also when we illuminate the atoms with a laser, if I impart momentum of the atoms with the laser, it's bad. So we need to trap them very tightly. And that's why we are going to develop what is called optical lattices. I'm not going to focus too much on that, but we trap them very tightly with light. And the other important part is that when we trap these atoms with light, something that is fundamental is that the frequency is not affected by the light itself. That's called a star shift, because when I trap my atom with light, it's going to fill up a potential. It's like it's going to, light introduces some type of confinement, yes? And then this confinement is important, that is identical for the ground and the excited. And that's why experimentalists have developed what is called deep magic lattice, such that I can trap the atoms and it's the same for the two states. So All of this, I will not elaborate on that. You will have to believe me because I wanted to enter in the part that is the many-body physics, that is the collisions. So we can discuss later in other times how they did that. But let's start to focusing on collisions. So what is the dilemma, as I said? More atoms, better signal to noise, but atoms, when you pack atoms in the same trap, they are going to start colliding with each other. And the problem is that the collisions is going to change the ticking frequency of my clock. What happens is that when I have more atoms, the ticking rate is going to be different depending on the n. This is the part that I'm going to explain during this lecture. How is this the ticking frequency of the clock depend on the many-body physics, and how we're going to do to suppress these errors. Because back when I started at JILA, 2008, actually these collisions were the second largest systematic in the clock. They were super bad. So we need to understand these interactions. On the other hand, I mean, I know many of you are interested in theories and interested in condensed matter. This is where I find it fascinating that atomic clocks can open a one-to-one bridge to many-body physics. And I can have a very simple explanation how we're going to do that. So if you ask someone about this, I mean, maybe Subir, if you are asked about strongly correlated materials, they're going to say they're so complicated because there is an intricate interplay between the spin degrees of freedom, the orbital degrees of freedom, and the charge degrees of freedom. Electrons, spin, orbital are really complicated. So the interesting part is that if you look at an alkaline strontium atom, as I mentioned, we have a nuclear spin, so we have this degree of freedom. The orbital degrees of freedom can be our two clock states. And even though we don't have charged particles, later in this talk, I'm going to show you that atoms in a clock behave as charged electrons because they do experience spin-orbit coupling. So we are going to cover that. But just as a motivation that understanding the many-body properties of atoms in the clock is not only good to make better clocks, but it's going to be good because it's allowing us to make connections with strongly correlated materials. Okay. Yes, I mean, I want to see, so it's like we're opening our eyes because what happens is that if we have a very good clock, we can understand the many-body behaviors better. We can resolve all the lines. And at the same time, we understand the many-body physics, we can guide clocks to become better. So we can make better clocks. Okay, so now I'm going to start very basic, and I'm going to remind you about the scattering in quantum mechanics. I don't know if you took a course when you were undergrad or graduate, but the idea is that when particles collide, the way that we visualize the collision is a scattering event. So typically we go to the center of mass and we are going to have one particle, they interact with a target, and then we look at the wave coming out the scatter. Yes, so you have an incoming plane wave, it scatters, and then at the end we have a spherical wave coming out. And the way that we characterize the collision is by the scattering amplitude f theta here, that is the incoming wave, I'm assuming along the z direction, and we will have this f theta, that is a scattering amplitude, that is an idea of the cross section. So there is an impact parameter, and we are going to see how is the cross section, the number of particles that are deviated at a given angle because of the collision. So the magic of here, we're, of course, quantum mechanics. What we need to do is to solve the Schrodinger equation of a particle. Now it's a single particle because we are going to go to the relative coordinates, and then the center of mass here is not affected by the collision, so we do a factorization, center of mass, relative, and then we're going to have a single equations for the relative coordinate, that's K. The center of mass is very trivial. So we define the reduced mass, that for identical particles is m divided by 2, that is the parameter that enters in the relative coordinates, and the total mass is what enters in the center of mass that we don't worry about. Okay, so we want to look at these cross sections that is associated with the scattering amplitude. So I'm not going to give a very, very detailed. We can read it later, or we can discuss it in during the tutorial, but I'm going to just summarize the most fundamental properties. So relative momentum is going to be quantized in quantum mechanics, is conserved. So we rewrite the wave functions in terms of what we call partial waves. That is a relative angular momentum from 0, 1, 2, and we sum over all of them. I don't know why this is not working so well. Maybe. Oh, the laser, here. Now I see. So there is the wave functions as the radial part with a given energy that is just k squared over 2 mu. And then we have the angular part that is satisfied by spherical harmonics. We know that spherical harmonics are what solve this equation. And when we put the spherical harmonic here, we have a centrifugal potential, L plus 1 divided by r squared. This is the centrifugal potential that it's going to accompany the potential that we have when atoms collide. When atoms collide, the potential is going to be very complicated. I'm trying to write a schematic of the potential, introduce the chemical bonding, is super complicated, but we mostly care about what happens in the long range part. And in the long range part, all type of potential are characterized by a van der Waals potential that has 1 over r to the 6 and with a coefficient that is C6. Well, the point is that I have this equation, these Schrodinger equations, the radial part, and the important part, that is the key simplification, is that energy and momentum are conserved. So you have a particle that are colliding, they collide, and after the collision, the only information that we care about the collision is a phase shift, because that's the only thing that can change because of conservation of momentum and energy after the collision. After the collision, they're not feeling any potential, so the energy and momentum has to be the same. And the only information that is telling me what happened during the collision is what is called phase shift, this delta sub L, and depends on the partial wave. So in the long range, there is only a phase shift, and if you solve the Schrodinger equation, I'm going to give you some notes, because some people might be interested in understanding how this derives. I will give you some notes. That after a while, this scattering amplitude depends on the theta, this polar angle. It's independent of the, we're going to assume a spherically symmetric potential and only the polar angle enter. The important part is that this scattering amplitude, when I write it in terms of partial wave, has a one-to-one correspondence with the phase shift and the k of the colliding particles. K is the wave number of the colliding particles that depends all the properties, because we only have k squared over 2 mu that sets the energy of the collisions. Yes. Well, to summarize, this is the summary. At the end, when we go to Hall particles, that means we take the momentum of the colliding particles to 0, because we're assuming ultra Hall. Then we are going to have what is called Wigner threshold loss, and this is going to be a one-to-one correspondence between the phase shift and some universal parameters that are called scattering length or scattering volume. So there are some specific parameters that is all what I need to know to understand the collisions. So if you can see this law here, the dependence of the phase shift with these parameters, we can see, well, the L equal to 0 is the channel that is the dominant at low energy, because it doesn't have any centrifugal barrier. Remember, the centrifugal barrier was L plus 1. So if it's L equal to 0, there is no centrifugal barrier, so it's the one that is dominate. So when you talk about cold atoms experiments, only the S wave, they are going to vote, only the S wave. But because we are super precise, we are going to need to start taking care about the P wave. The P wave is the L equal to 1 collisions. So as I said, the L wave, the L equal to 0 doesn't have any centrifugal barrier. The L equal 1 have centrifugal barrier, that in the case of strontium is the order of 30 microkelvin. So if we cool our atoms to 1 microkelvin, this barrier is super large. And that's why June, this is super large. Now, Fermi statistics is going to be our salvation. Why? If you have identical fermions, the wave function has to be antisymmetric, and therefore they cannot be at the same position. And therefore, S-wave collisions are forbidden for identical fermions. The only channel that is allowed for identical fermions is the P-wave channel. And the P-wave channel cost energy because of the centrifugal barrier, 30 microkelvins in strontium. So Jun is a very small person I have not introduced to you. Jun Ye is the clockmaker, is the person who makes clocks at JILA. It's amazing, and we have done a lot of, it's really fun to collaborate with. And of course, when he joined JILA and was building his clock, he said, I like fermions. I don't want collisions. I'm going to build my experiment with fermions. That's where fermions are so important in this story. Okay, so now I'm going to have a joke because add some distraction. I don't know if you have heard the joke about the spherical cow. So this story tells that there was a farmer that the cows were not milking, the milk was bad, and he hired a psychologist, then an engineering and a physicist. So the psychologist asked him to paint the walls green so the cows can be happy and relaxed. The engineering said that no, he needs to change the milking machine. And then it came the physicists, and the physicists started look at the cows, and then they start to grow in the blackboard. Well, imagine that you have a spherical cow in vacuum with a symmetry production of milk everywhere. So we're going to do now a spherical cow approximation of collisions. That's what we like. We are physicists. We are going to move to our spherical cow. And the hero of that story, I don't know if you know that he died a few months ago, Professor Yang Chen Ning. So what we are going to use is what is called Huang-Yang pseudo-potential. This is key. This is our spherical cow, if I can. These are going to be, yes, of course.
So you're saying that we need to use P-band. I think my voice is quite loud. You were using the P-band because of
it's not band. It's
P-scattering.
P-scattering, P-wave collisions, P-wave channel.
Yes, but all of these work with the fermions, which is like a lot of things. Like, why don't we just, like the S-wave collisions in strontium 88 is already -2. Like there is no chance to have collisions like.
Yes, the problem, as I explained before, is that the strontium 88 doesn't have a transition.
Yeah, because of you need like super large magnetic field to open the transition. You need a super large
magnetic field, and you add as much noise as you have. It's complicated. No one has a very good strontium 88 clock with large number of particles.
I see.
Good point. Yes, yes, yes. So yes, if we were finding an atom that doesn't collide, that would be the best. But at the moment, no. And that's what we have to deal with. So going back to our spherical cow, what we learned from these very smart guys is that we don't need to understand the potential of the collisions of the atoms because it's super complicated. But the only thing that we need to know is the scattering length and scattering volume. And we can do, in order to write the physics, is we construct a pseudo potential. That means a potential is extremely simple, a delta function potential. We replace this complicated atomic potential that I showed you before by, maybe I will change it, by a delta function. I mean, you can see in the blackboard. And the idea of the pseudo potential is that when we write the pseudo potential, I will give you the notes. It's complicated, but the pseudo potential has an expansion in spherical ways that is, well, it's complicated. I will give you the notes. But the important part here is that for the pseudo potential that is trivial, a delta function up to some regularization because we don't want to avoid infinities, what happens is that for the pseudo potential, we only need to write in momentum basis a constant interaction term. That's it. Instead of having a complicated formula, it's a constant in momentum. And for the P-wave collisions, the pseudo potential give me matrix element in momentum space that are just k dot k prime. Very simple. So this is the form of the potential that I'm going to put in my many-body theory to do the calculations. This is extremely simple. A constant or something that is quadratic in k. That's it. So that's what we're going to do the calculations. And I will give you some notes again for details because I know that its formula is awful, but you can derive it. Okay, so now let's go think about collisions for alkaliner atoms. And then we're going to have also a very important point that I emphasized before. For the j equal to 0 states that are the clock states, if we ignore all complicated higher order um, matrix elements from the hyperfine interactions that are allowed the couplings, then what happens is that for j equal to 0 states, I dot j is equal to 0. What does that mean? That the nuclear spin, I, is not coupled with the electronic spin, j. And if they're not coupled, when two atoms collide, the collisions enter from the electronic part of the wave function, not from the nuclear. The nuclear isolated. So that introducing some type of unique symmetry in the collisions that is just physically means that the collisions are totally independent of the nuclear spin. They don't depend on the nuclear spin because I dot j is equal to 0 for these atoms. So that means that if two, let me try to do the cartoon, if two atoms in two hyperfine states, 9.5, 7.5, collide, after the collision, you have to remain in the same type of a hyper, I don't know why, you cannot change this, changing the nuclear spin doesn't work. You have to conserve the nuclear spin. That's fundamental. So now the symmetry, there is an n, and I'm going to explain now in the blackboard because this is important. The symmetry is set by the number of collisional nuclear spin channel in my system. In the case of strontium, the symmetry n is equal to 10 because I is equal to 9.5. So the SUN symmetry is that nuclear spin independent scattering parameters. The scattering parameter doesn't depend on the nuclear spin because the nuclear spin doesn't participate in the collision except from the Pauli statistics that we have to satisfy that. And there is no spin changing collisions. That's the key. So let's try in the blackboard to understand a little bit of what I mean by SUN because it sounds like a very complicated object. So for that, let's start by SU2. So SU2, when you think about SU2, is something that is in the Bloch sphere, is spherically symmetric. That means I don't know if I am up or down or it's spherically symmetric. So the way that we characterize collisions that are SU2 symmetric, like Subir was writing for the Hobart model, the collisions, the Hamiltonian that describes the collision has the form S dot S. And for example, we are going to say for the case of, we are going to consider, for example, just a spin up and down. That's it for the moment. Let's imagine only a spin down but now. And then if we have that, if I have from Pauli exclusion principle, the wave function for the fermions have to be antisymmetric. So I only can have up, down, minus, down, up. This is a singlet state. So I mean, in triplet state, I can have an additional degrees of antisymmetrism, but so in this case, imagine that I have a Hamiltonian in this form. So if I have triplets, I can have some, I can put a minus sign. When you put at this singlet state here, I get a minus three quarters. And the minus 3/4, I get some interaction. Let's put this here. I get an interaction U. The triplets, all of them has 1/4, and they don't interact. These interactions are SU2 symmetric. You can see here, this term doesn't care if I am in any orientation, it's a scalar. And what it means is that this operator commutes with total Sx, total Sy, and total Sc. So I have this Hamiltonian, and if you look at all the generators of my Hamiltonian, this commutation is 0. That's what it means that is SU2 symmetric. So when we go up SUN, it's going to be exactly the same, but in a bigger Hilbert space. So what happens, I mean, here, when you write this Sx, Sy, Sc, I mean, or in terms of Pauli matrix, maybe better let's put S plus, S minus, and Sc. These are going to be operators that are associated with up, down, or up, down. Yes, this type of couplings. For SUN is easier. That type of representation is called fundamental representation. And if we are going to have n flavors, n flavors, in this case, this n is the number of flavors, then my fundamental representation operators for an atom I is going to be an operator that is like this. Yes? Change m to n, similar to here that you change here. And a Hamiltonian is SUN symmetric if I write my Hamiltonian as somewhere I, J, U. I'm going to ignore this constant. I'm going to have S, N, M, I. Then I can put even here S, N, M, J. This Hamiltonian that is a summing is equivalent to have a Hamiltonian of this form. And the important part is that this Hamiltonian H is going to commute with any generator. So you're going to have sum over I, S, N, M, I. Like in this case, you are going to commute with any of the generators. So you have n squared minus 1 generators, except including, I mean, I'm excluding the identity because it's trivial, and all of them they are going to compute. So when we are going to write our SUN Hamiltonian, we are going to write something like this. And the important part, as you are going to see here, is that quantum statistics start to matter a lot. Because, for example, as in this case, only the singlets are allowed. So similar in this case, if we are going to have fermionic statistics, we are only going to have something like this in this form, singlets, SUN, and this is not exactly an SUN singlet, but antisymmetric states. So that's important. So this is the Hamiltonian that we're going to deal when we are going to write the collisions of alkaline atoms. Now a little bit of information. What is the approximation that we do when we do this SUN assumption? So what matters is that the scattering length, for example, for S-wave collisions, needs to be independent of the nuclear spins. That means SUN symmetric, a scattering length independent of the nuclear spins. This is, for example, different for the case of alkali atoms. So I don't know if you have heard about experiments of alkali atoms where you are going to write, for example, for F equal to 1 alkali atoms like rubidium. When two particles collide, you have an F equal to 1 guy and F equal to 1 guy. They'll collide, and the possible channels are F equal to 2, actually F equal to 0 because it's not allowed by Pauli statistics, and you have these two possible channels, and you are going to have a scattering length that you write a scattering length that is A2 and A0, and they're different, not the same. And in this type of atoms, for example, you can have something like you have an atom here. This is F equal to 1. This is therefore minus 1, 0, and 1. These are the MC components. And you can have two atoms in M equal to 0 collide, and this go here, and this go here. It's allowed because the total magnetization is conserved. Minus 1 plus 1 gives you 0. But you are changing the hyperfine levels. This is completely forbidden in alkaline atoms. This cannot happen. Collisions, there is the symmetry, and we have a single scattering length. So some of the arguments that we gave to explain that, and just maybe some information, that the difference in a scattering length between the different nuclear spin states is proportional to the potential, the difference in potential in this collisional potential that they have. Remember, I mean, we are replacing that by a scattering length, but typically this, there is, I mean, we know that there is a potential, and this in the different potentials times the time that the atoms are during the collision. This time of the collision can be of the order of picoseconds. And this delta B of the potential is going to be some type of matrix elements that are coupling the nuclear spin states because of the hyperfan interactions. Yes, so this delta B is going to be associated with a coupling. For example, if we have 1s0 and we have 3p0, 3p1, and so forth. So in this case, it's going to be a coupling matrix element between these two states. Yes. So it's a matrix element square divided by the energy difference, like second order perturbation theory. And when you compute this times this time t, all this delta B, this is delta B, you find that this, we computed this is of the order of -9. Tiny, tiny, tiny. So really you are satisfying this symmetry at the 10 to the -9 level. You repeat the calculation for the case of the not 1s0 but 3p0. This number is reduced for, this is 1s0. For delta A divided by A for 3p0, it's of the order of 10 to the -3. The difference is that in the 3p0, you already have couplings, direct couplings. It's not second order perturbation theory, but it's more first order perturbation theory, and you get a number that is 10 to the -3. But it's still remarkable. I mean, I'm fine because condensed matter theories always dream to have SUN symmetry in their Hamiltonians, and we have it almost perfect. So that's very nice. And this is going to tremendously simplify the treatment of the collisions that we have for alkali atoms. Okay, so now, yes, and we have n up to 10. That's a dream. Okay, so now let's start discussing the theory of the collisions. Even what I wanted to say is that even though we have SUN symmetry, the collisions are still complicated because we need to worry about S wave, well, in some cases, I mean, I will explain why, but typically P wave when you have nuclear spin polarized atoms. And even though we have a single parameter that is independent of the nuclear spin, in order to model the physics, we are going to deal with 8 different scattering channels. Why? If you have S-wave collisions, for S-wave collisions, again, I mean, let's go back to explain very clearly what happens. So, as we said, we are going to have, we have fermions, yes? So, because we have fermions, we have to have a wave function that is totally antisymmetric. For S-wave collisions, is L equal to 0. So the spatial wave function needs to be symmetric. In order to have an S-wave collision, you have to have a symmetric spatial. That's spatial. So this is spatial because it's L equal to 0 collision. So because of that, in order to have the other possible collision, part of the wave function needs to be antisymmetric. That's why for identical fermions, I cannot do it. But if I don't have identical fermions, then I can do it. So for now, if I have, for example, atoms in the ground state, yes, then I have to have a singlet channel in the nuclear spin. And this channel has an interaction that is, or a scattering length that is 8GG. Now, if I have EE, same story. I have to have a singlet, and I'm going to have a scattering length that is 8GG. Now, I can also have a triplet here. It has to be a singlet, and then I have a scattering length that we call it AG+. And this is what I'm trying to enumerate here. So AG+, so you see the game. Now, if I have here above, I can have EG minus EG. In this case, when I have EG minus GE, what happens? This has to be symmetric, yes? And we have a scattering length EG minus. So that's what I'm dividing here between nuclear spin symmetric and antisymmetric. And you can see that for the S wave, I have these 4 scattering lengths. And for the P wave, I'm also going to have 4 different scattering volumes. Similar story. For the P wave, the difference is that because it's L equal to 1, the story reverses. For L equal to 1, then the wave function has to be antisymmetric. The spatial wave function has to be antisymmetric. And therefore, the remaining part has to be symmetric. Yes, for example, I have to have GG and symmetric nuclear spins. And this is going to characterize by a scattering volume BGG. Okay, so this is going to have it in mind because we are going to start playing with that. Okay, so the first example, I'm going to start very simple. We're going to solve what are the collision properties of 2 atoms in an harmonic oscillator. 2 atoms in an harmonic oscillator. So let's imagine at the moment that we are going to start dealing with a spin polarized. So all the atoms are spin 9 half. So forget about the nuclear spin for the moment. So if I have then to label the states as I was labeling here, we have the singlet state, and then you have a symmetric spatial wave function. These are the harmonic oscillator modes. We know that in an harmonic oscillator, the eigenstates are quantized, are discrete, and therefore this is the spatial wave function. If I have triplet states, then these are the symmetric EE, GG, and EG plus. We need to have a wave function that is antisymmetric. Yes? Now, if I write the matrix element, and these are the corresponding interactions, AG minus, BGG, EGG, and BG plus. If I write the matrix that characterizes the collisions in these atoms, then it's going to be, of course, a 4x4 matrix because I have 2 atoms, yes? So this 4x4 matrix, I'm going to have different scattering volumes. These are associated with the P wave component. That there is S wave component that is only from the singlet state. And I sometimes, if I remember that I'm going to have, remember when I was writing SC in the blackboard before for the Ramsey spectroscopy, the C is going to be delta and minus delta for the states that are spin up, both up or both down. G is down, E is up. And the states that are T equal to 0 and singlets, they have delta equal to 0 because the sum of SC is 0, yes? So now, in the presence of the laser that is going to couple ground to excited, what happens if the laser is identical for the ground and the excited, then triplets couple to triplets and they cannot couple to singlets, yes? So in this case, for example, the state that is here, T minus, that is ground, is going to be connected to E plus G in the triplet manifold. This is omega. The state that is this one, that is E, is going to be connected by here, and the singlet remains isolated. Yes? So therefore, if you have atoms that are nuclear spin polarized, and then we have identical Rabi frequencies, the singlet is decoupled. And we have only P wave interactions. So the first time where the clock was operating, it was seeing collisions. It was seeing shifts because of the interactions. And it was very confusing because how can it be if the P waves are so weak? How can it be? Remember that the barrier was 30 microkelvin and the clock was operating at 1 microkelvin. How is that we see these P wave interactions? So at the beginning, we were a little bit confused of that, and I think the answer is that the clock was so precise that peak wave interaction even are important. But at that time, we were trying to figure out a source that can couple the initial triplet state to the singlet. And one of the sources that we thought could be the case is when the Rabi frequency that experience atom 1 is different than the Rabi frequency that experience the second atom. Because if that's the case, then you can open a coupling to the singlet state. Yes, if you have, if the atom 1 and atom 2 have different Rabi frequencies, then you can start coupled to the singlet state, and therefore you are going to start experiencing some type of collisions. And it was a lot of work trying to figure out that, but at the end we discarded that possibility. And we realized that actually no, it was no different in frequency. So at least that's good. So and now we worked out the problem for 2 atoms. Now we're going to start cranking the complication, and we're going to go to solve for many atoms. And when we start solving for many atoms, we need a more sophisticated formulas. So we go, and bear with me, it's going to start a lot of equations, but we're going to try to understand it step by step. So when you're going to look at many atoms, we are going to write a field operator. Yes, a field operator is an operator that, for example, phi alpha m is going to be a field operator that destroys an atom in a orbital state alpha, spin nuclear spin m, and position r. This destroys an atom. So, and these operators, because are fermionic, satisfy the standard fermionic commutation relation. Yes, the anti-commutation. So now, okay, this is I'm going to write the Hamiltonian, the many-body Hamiltonian that describes the physics of many atoms that are interacting via S-wave and P-wave collisions. So let's look at this Hamiltonian first. The first term is the kinetic energy, and the potential is the single particle term, when you are going to have here the kinetic energy, and for example, if you have a trap from the lasers. Now, here, you are going to have collisions between the ground and excited states. So, because we are writing these operators that already satisfy the fermionic statistics, it's much easier to write it. So this operator takes into account of the fermionic statistics already, and just is a collision between the ground state, Ng. I mean, maybe I can have this is the definition of the actual density. So it's the number of particles in G at position R, and the number of particles in E at position R. This is the standard scattering between this. Now, I don't know if you have seen how you characterize P-wave interactions, but remember that I have K dot K prime. And K in position space is just going to be a derivative, or actually, in this case, it's going to be a divergence, because it's going to be this dot this. So I'm going to have this term that is going to have a K, and this term that is going to have a K prime, and this is the form of the P-wave interactions. Yes, we are going to write this Hamiltonian, and our exercise later is we are going to work mostly with this term, because as I'm going to remind you, if you have a spin polarized states with same, and we are interrogating by a laser that doesn't couple to the singlet, these collisions are not going to be important, and we are going to only deal with P-wave. Okay, so what has been the key for modeling the interactions in the clock? The key is that interactions are weak, in contrast to other talks that are very complicated. Here, we're going to deal with collisions that are super weak, and perturbation theory actually works. So what is the leading Hamiltonian is the single particle Hamiltonian, and collisions are going to be treated as a perturbation. So what I'm going to do is that I'm going to write the field operator that, now I'm going to remove the M. I'm going to only work with nuclear spin polarized particles for the moment. I'm going to write my field operator that destroys a particle alpha at position R in terms of fermionic operators that are eigenstate of the single particle potential. And actually, when you have particles, I'm going to imagine, I mean, what happens is that the 1D optical lattice clock utilizes a very deep 1D lattice. So the atoms are going to be trapped in a very deep 1D lattice. And it's going to be so deep that the atoms are not going to be able to tunnel. We are going to later deal with the tunneling. At the moment, not tunneling. So each of the atoms are going to be in a single lattice site, and we are going to imagine a single lattice site as an harmonic, a 2D harmonic oscillator. So it's going to be a 2D harmonic oscillator. In the third direction, that is along the T direction, this is the C direction, I'm going to assume that my particles are going to be in the ground state here. Ground state along the C direction, and along the XY direction, I'm going to have an harmonic trap. This is 2D, and I'm going to have levels that are NX and Y. These are the harmonic oscillator levels, and I'm going to expand these into, these are mid polynomials that characterize the eigenstates of single particles in an harmonic oscillator that is 2-dimensional. Yes? Everyone with me? Now what I'm going to do, and this is the harmonic, their mid polynomial. What I'm going to do is that I'm going to write this inside the Hamiltonian. I'm going to write, remember these field operators, I'm going to replace these field operators into this Hamiltonian. And when you do that, what happens is that you are going to have a product of 4 operators. And these are going to be matrix overlaps of the different wave functions here and the derivatives that I wrote for the p-wave interaction, yes? So when you do that, it starts to be scary, but you have, for example, remember that we have something that was something that was a divergency. So you are going to have delta dot delta, yes? So you are going to have something, I mean, and we have wave function here, and we have wave function here. So for example, so you are going to have something that is dx, some wave function here, dx, some wave function here, but the other part, the other components, doesn't have any derivative. Then we're going to have plus, so these are going to be the component of along the x direction, and then this is multiplied maybe by something that doesn't have derivative. So you are going to have wave functions that are along the other directions. 2 minutes? One, okay, perfect. So yes, bear with me. So these are the matrix elements. You can see here that is a product of this 4 Hermite polynomial, and then for this term, you are going to see derivative here, derivative here. Everything can be computed. I mean, it's messy. Everything can be computed. But then maybe I will start next time to show how this simple model is going to tell us how to deal with the collisions of the clock in spin polarized atoms. So you now have all the machine. Then we're going to go with the actual calculations and show how we're going to guide the clock at operating at a specific point where collisions are not going to be bad. Okay.